Hello, everybody, and welcome to another wonderful day of chemistry. So previously, we were looking at weak acid, strong base systems. We're trying to find some information about a weak acid analyte. However, today we're going to kind of flip that on its head and try and look at some systems where what we want to determine is some sort of information about a weak base. So one of the best ways to do this is, again, like before, using titrations. This is often useful if I want to try and determine the pKa or the concentration of something like ammonia, which is present in many household cleaners, sodium acetate, sodium benzoate. A lot of very common food preservatives occur as weak bases. However, in order to determine information about them, they will need to occur as our analytes, so what we place in our beaker. And if I add a strong base to this, I'm just going to end up making a very basic system. So in order to get as much information, we have to slowly protonate these systems to form a weak acid-base set. And to do that, we're going to need a strong acid to make sure we completely and quantitatively convert some of our weak base into its conjugate weak acid. However, just like before, when it's important to standardize your sodium hydroxide, in this case, it's very important you standardize your strong acid. And again, HCl is a good example strong acid to use. So in general, these titrations can be treated very similar to our weak acid titrations, but one of the most notable differences is that in a weak acid titration, our pH increased because we were adding a base. In this case, our pH will decrease as we're going to make it more and more acidic. So let's go ahead and look at an example system. So let's say that we're adding HCl to 25 milliliters of ammonia. So ammonia is a nice counterpose to acetic acid. As acetic acid has a pKa of about 4.75, and ammonia has a basic pKa of about 9.25, which will come into play here shortly. And so as I'm adding HCl to ammonia, we're going to start with a very similar treatment to our weak acid system. The first thing you're going to need to do is perform an ice table to try and figure out exactly how much of the ammonia has been converted into ammonium via protonation by HCl, remembering that this reaction will go to completion. So using that information, we can identify which of the 4 key regions on our titration curve will be present, and that will determine what sort of equations we need to use to determine the pH of the system. So the starting point is going to be trying to, as before any acid has been added, all I've got is a weak base. I've got ammonia. So in order to do this, we can go ahead and calculate the hydroxide concentration using the initial concentration of our base and its equilibrium constant. So again, this will be the product of having already performed an ice table on our weak base. From here, you can turn the hydroxide concentration into a pH. So the next key point is I will have converted some of my ammonia into ammonium and generating a weak acid-base pair. So based on the exact ratio of HCl added, we can either have more base present, at which point you'll be above the pKa, or you can have more acid present, at which point you will be below the pKa, as you'll have produced an excess amount of ammonium. With again the very notable point where exactly half of the ammonia has been converted into ammonium, at which point you've reached the halfway point, so cleverly named, and the pH will equal the pKa. So from here, we can end up adding one full equivalent of our HCl. At this point, all of the ammonia will be turned into ammonia, and we will have a simple weak acid system because the only acid-base component present will be that ammonium weak acid. And from here, you can determine the proton concentration based on the concentration of the weak acid formed and the equilibrium constant for that weak acid decomposition. And then similar to a strong base system, you can end up adding an excess of acid. at which point you're in this strong acid region, where the pH is exclusively controlled by how much unreacted HCl is present. And you'll notice that as you keep adding more and more HCl, it will slowly converge on the pH of that pure HCl system. In this case, with a 0.1 molar HCl concentration, this means we will converge on a 0.1 molar proton concentration, or a pH of 1, as you can kind of see here. And so just like the weak acid system, it's possible to calculate the pH at every step along the way to generate an idealized acid-base curve. And one of the things I do like to emphasize is that you'll notice the pH will change fairly slowly in the buffer region, as the buffer will help control any sort of pH change, and fairly slowly in that strong acid region, as we're mostly looking at the concentration of just strong acid in essentially less and less diluted water. However, it is also worth noting that one of the big key features of all three of the titrations we've seen so far, strong acid, weak acid, and weak base, is that the pH rapidly changes near the equivalence point. So once we have that near equal amounts of acid and base, we tend to see rapid pH changes. And next time, we're going to go ahead and take a quick look at indicators to see how we can make that work in our favor. Until then, take care.